Hello class, this is Ms. Riggins with today's video on section 2.3, Piecewise Defined Functions. Please remember that as you're watching the video, take down important notes, equations, formulas, or statements that I make. And don't forget to feel free to pause or rewind as you're watching the video 1, 2, 3, 4, or 5 times. Also, at the end of the video, write down your summary about the video and then submit that in your question online. Let's begin. Piecewise defined functions. If I were to ask you what type of function this graph is, some would say, oh, it's a quadratic, and some would say, oh, it's linear. Well, it's a combination of both, and this is where we have a special type of function that is defined by pieces of other popular functions. So a function with different formulas for different parts of its domain is called a piecewise defined function. So in this particular case, we have two functions. We have a quadratic function, and then we have a linear function. And the thing to note about these functions is that they can be defined in two different ways. This particular function can be defined by the equation y equals x squared, and this particular function can be defined as the equation y equals 6 minus x. But it's important to note that it's not the full y equals x squared graph, and it's not the full y equals 6 minus x graph. And that's why we call it piecewise defined function, because they're pieces of a graph. To describe this analytically, there's a particular type of notation that we should use when we define piecewise functions. And that looks like this. So here we have y equals, and then we have an x left curly bracket. Okay, that defines that we're going to have pieces. And in this case, we have two pieces, but we can have as many pieces as we want. And for each piece, we're going to write the equation or the formula that defines each piece. In this case, x squared. In this case, wrong color, 6 minus x. But the important part in piecewise function is defining for which parts of the domain are we going to use each formula. So as we can see here, we use the quadratic formula all the way up until x is equal to 2. And then we use the linear part all the way up until from 2 on. And this is why it's very important when you write piecewise functions. It's not enough to just have the formula. You have to identify when you're going to use the formula. Now I know you're talking about, oh, I see range up here. And the reason why you see range up here is because the next question would be, how do we describe the domain and range of these functions? And so we're going to start with the domain first. And because to me that's the easiest. All you have to do to identify the domain of this function is to look at this part of the piecewise definition. Which values are we using to define this function? And as we can see, we're using x values less than or equal to 2 and x values greater than 2. Well, that includes all the numbers on the real number line, so the domain is all real numbers, or from negative infinity to infinity. Now someone might say, what if we don't include one of those numbers? So let's say I get rid of this. Well, in that case, I no longer have a way to determine what the function output is when x is equal to 2, because both of these formulas are only used for values that are not equal to 2. In that case, we would have a hole in our graph because there'd be no function value for 2, and our domain would be all real numbers except that are not equal to 2. Okay? But in this case, our domain does include 2, so we still have all real numbers. But the range is a little bit tricky because, as we can see, for this particular function, y equals x squared is a quadratic, and it has all of its output values are greater than or equal to 0. So I can say, okay, well, the range of the quadratic is from 0 to positive infinity. And then I can say, oh, this part of the formula is a linear equation, and a linear equation has a range of all real numbers. And that would be okay, but if you remember that we can only use x squared for x less than or equal to 2. Well, so that still holds that the range for this would be from 0 to infinity, because as we can see here, this part will continue on and on and on to infinity. Oops, wrong color. And this part stops, but that's okay because we already have all these values over here to the left. But what's important to note is right here for y equals 6 minus x. We can go all the way down to negative infinity, but we stop right up here, whatever this value is. And when I plug 2 into this part of the formula, I get 4. So the actual range for this part, for the range, would be from negative infinity to 4. So this part is from 0 to infinity, and this part is from negative infinity to 4. But together, they cover every single number on the real number line. Because as you can see, there are y values from to the left or to the right of every value on this equation, sorry. So in this case, the range of this would be negative infinity to infinity, all real numbers. All right. So let's take a look at one of the most popular piecewise defined functions that you've already been working with but didn't realize it was piecewise defined functions, and that is the absolute value function. Absolute value function is really originally a piecewise defined function. We use a particular notation with the bars to indicate its absolute value, but the absolute value basically means this. The absolute value of x is, for one piece, the formula x for x greater than or equal to 0, and in the other piece, the formula is negative x for all x values less than 0. So the absolute value function is really a piecewise defined function. And as we can see, the domain of this function is all real numbers, because all x values can be plugged into this equation and get an output. And the range is all positive numbers, including 0, because as we can see, for all values greater than 0, you're going to have a positive answer output, and for all values less than 0, you're going to have a positive output for this piece of the graph. So this is an example of a popular piecewise defined function. All right, that's it for the video. Hope you enjoyed it.